For today is to work through the AP problem that you see before you. And following that, we'll talk about the grading of it and how we get marked up. And then according to how much time we have, we'll go through other sample student answers and see how those students would have fared.
Wait, but this is the actual AP test.
Uh-huh. This was the test given in 2005. They, I want to say between 2003 and 2012, they gave forms A and B as a way to try to cut down on cheating. Because what was happening is people were taking it on the East Coast and like surreptitiously taking pictures and then sending those to friends in Hawaii or whatever.
It's like a lot of
Yeah, exactly. Nowadays, they do it slightly differently. There are going to be two forms given randomly.
Not A or B.
Not A or B. So it used to be like a given school was going to be an A or a B. Last year, students came out and said some of them had form H and some of them had form J or something like that. And so there were two different sets of questions.
Isn't that just the same, just different letters?
It's the same, but it's throwing an element of randomness so that you cannot guarantee which form you have.
You mean like our school will have H and J
Correct.
rather than ours?
Yeah, students in our school.
Okay,
Said we have different forms. So there it is. Now what happens is you have 6 of these questions, and these questions are given over a 90-minute time period, so that works out to 15 minutes per question. And it is standard that some questions are going to be easier for you and some questions are going to be harder for you. So the right way to do this is to go through and do the easy ones first. Somebody tell me why that's a good strategy.
Because then you won't be wasting your time on hard ones.
Exactly. You don't get sucked into hard questions, but there are other reasons. Why else? That's right. It's a video game strategy. You're picking up as many points as possible quickly. And one more reason. How many of you get nervous when you take tests? How many of you feel better when you look at the first question, you go, I can do this, right? So if you do the questions first that you're good at, then that helps calm your nerves and helps get you into the groove so you can say, I can do this. Right? So for that reason, we want to get really good at these area volume problems because you know what? Every year since 1963, there has been an area volume problem on the test. So it's a pretty good bet that there will be again this year. So we want to make sure that we're good at these. Okay. Now, tonight for your homework, you've been assigned some AP problems, and I want to show you where to find them. If you go to Edline, and you go to the calculus page, which does not say hello, Dolly, but instead says the fundamental theorem of calculus, which finally makes sense, right? And if you go to the link over here that says AP Central, and I'll actually put that, I'll put that in your news feed so that it shows up here. And you click on that AP Central link, you now go to the College Board website that gives you information about all of the exams. Now, fortunately, we are not taking Studio Art 2D Design, so we're going to ignore that one, and instead we're going to click on AP Calculus AB. Ta-da! And when we do, the link takes us to free response questions. All the free response questions that ever were from 1998 onwards. More than you could possibly work. Okay. So here are the questions. And the questions, it's a little hard to see. Let me expand this. Doop, doop. There we go. The questions come in PDF format, and they also give these scoring guidelines. Some of them have some questions and answers about student performance and scoring statistics so that you can see. If we have time, we'll take a look at the scoring statistics. I think you'll be delightfully pleased. And then we have some sample responses and then the score distributions for that year. for the, I think it's for the exam overall, but it might break it down into multiple choice and free response. So here's how you use this. Tonight you're assigned to do, I think it's 2004 number 2. So you would scroll down until you get to 2004 number 2. There it is. Be aware that there, between 2003 and 2012, there's an A and a B.
Oh, it's 2005, Form B.
That's the one we're doing in class. Your homework is going to include 2004,
Oh.
right? So make sure that you're not doing the B form here. When you pull it up, if it is Form B, it will say Form B across the page, and then you'll know. Okay. And so you'll pull up the free response question. You can print it out if you want to, but you can also just work it on paper right there if you want to. There we go. And then once you've done it, then you scroll down to the appropriate question. There it is. And look, it's an area volume problem question. And you're going to work that area volume problem. If you want a challenge, try to give yourself 15 minutes for it. But if it takes you longer than 15 minutes at this stage of the game, don't worry about it. That's cool. I would rather have you take your time and think it through. Go work on getting, being quick on it later. But here's the secret. The more times you iterate something, the faster you get it at, right? We've all found that to be true. The first time I learned how to use a potato peeler, I was slow. The second time I learned. The third time, let's go right. Once you have worked the problem, we need to check. Absolutely. How do we check? Well, we go back to the scoring guidelines. And the scoring guidelines tell you not only the correct answer, but also the number of points that you would have gotten for each thing. When we work the problem here, we're actually going to walk through the scoring guidelines and see how all that works. Okay? You are going to score your paper once you have worked the problem. I don't care if you get 5 out of 9 at this stage. Of course, I'd love for you to get 9 out of 9. But the important thing is for you to see for yourself any mistakes that you made and to learn from those mistakes. So every year I've got a couple students that think it's going to be a smart idea to just skip the working of the problem and I'm just going to copy down the stuff from the answer key. Okay, you can do that. And you learn what from it? Absolutely nothing. All right. Does this make sense to everybody in terms of process? Awesome. Here's what I'd like for you to do. I'd like for you to take a look at the problem in front of you, which is 2005B, number 2. And we're going to talk our way through this. We have f and g given by the functions f of x equals 1 plus 2 sine 2x, and g of x equals x over 2, that R be the shaded region in the first quadrant enclosed by the graphs of f and g as shown in the figure above. All right, first question we have is, can I use the graphing calculator on this problem or not? How do I know? Oh, the directions say so. That's exactly right. The numbering is a little bit tricky. For 1998 only, you could use a calculator on all 6 problems. For 1999 through 2014, you could use a graphing calculator on problems 1 through 3, but not on 4, 5, and 6. And for last year, you could use a graphing calculator on problems 1 and 2, and not on 3, 4, 5, 6. Rather than have you remember all that, on your homework assignment, I've given you a helpful little notation that tells you whether or not to use the graphing calculator. If you take a look at your homework, it says GC or N. GC stands for, and N stands for no calculator. Right. I didn't put NC because some people might see the C. Trying to be helpful. So this is a calculator problem, and because it's a calculator problem, that means that I'm going to use the calculator to do what? What am I going to use the calculator for? Intersection points and integration. I'm going to be dogmatic about this and say that not only can you use the calculator for these things, but you should use the calculator for these things. On the calculator section, you should be using the calculator to do intersection points and integration. If you want to do it by hand, because you've got lots of spare time, you can do that, but you'll be taking time away from something else. See what I'm saying? So in terms of efficiency, we want to do that. All right, so now they sketch the region for us, helpfully, but unhelpfully, they don't put everything that should be put. What is missing in my region? Intersection points. So that's the first order of business. Find that intersection point. Go. Yes. When are you going to get your own? What's the first trap that we need to avoid taking a look at f of x? That's maybe too vague. What mode should we be in? Radian, not degrees. Yep. So you got to check that, especially if you're in physics. I have had students do things in degree mode, and they were tears. Okay, what'd you get for the intersection point? Samantha. One, 6, 4, 7, 6, 4, 5. Yeah, good. That 4 places is really necessary here because if I rounded it to 3 places, then I would introduce round-off errors in my area, and then I would actually not even be correct in 3 places, and then I would lose the answer, and that would be my score. So the 4 places is really crucial. Okay. What else needs to happen before I get going on this? Well, maybe I should look at A. A is asking me to find the area of R. So what is needed on my sketch here? Yeah, the representative rectangle. Question, should I do it horizontally or vertically? I can do either one, but one's a clear, better choice. Which one is a better choice here? Vertically, why? Yeah, because y is given in terms of x. And therefore, I want to do dx's here. So I'm going to do my vertical rectangle right there. And there's d, and I'm going to label that as dx. And so, I think I can go ahead and write the area integral. James Perry, give me the area integral. Excellent. Now, let's just check real fast. Did he do top curve minus bottom curve? Yep. Did he do first x to last x? You sure he didn't do y? Check that. Yep. You just want to make sure you do x's and not y's because your integral is in terms of x's and not y's. That's very good. And now, how am I going to compute that integral? Directly on the calculator. Go. When you plug in y equals blah, blah, blah on the calculator, it will not look like you're reading. Because it is what y is here is the difference in heights between these two. So what you're going to be looking at is something that is the difference in heights between the two curves. It should be 0 at 0, and it should be 0 again at 1.257. What do you get for your area? 0.4290. Do your grader a favor. In some way indicate that this is your final answer. Double underline is good. Boxing is good. Putting a smiley face next to it is a little cheesy. But you can do that. Yes?
Can we use the rounded value for
A rounded value such as 0.43? Oh, here.
Yeah.
Like 1.13? Something like that?
No. I mean, the value is 1.1256. Can we use the rounded one?
Well, let's answer that question by experimenting. You integrate from 0 to 1.1256 and tell us what you get. You integrate from 0 to 1.1256 and tell us what you get. You did. What did you get? Do this. Integrate this from 0 to 1.1256. Do that. Now, taking a long time. Oh, you didn't integrate the first time. No.
Mr. Cagle, shouldn't the intersection point be 1.1357?
Well, okay, do we have the wrong intersection point?
Instead of a 2.
Did you do the intersection point? Who did the intersection point for us? Did it say intersection? It said intersection.
I mean,
Did yours say intersection?
mine do. No, I just did intersect this way.
How?
That intersect.
Yeah.
Here, over here.
Yeah. 1.1357.
Yep.
Oh, did I hear you wrong?
Yeah, I got it.
Oh, speak up. Tell me if I hear it wrong. Okay. So does that change the value of our integral then?
Slightly.
How much? Okay, fair enough. Kenneth, was that your question? Is that what you were asking about?
No.
Okay. All right. Did anybody else have a weird thing with intersection points? In the future, don't let me go on like that, because that confuses people in videos. Yep. Okay. So if you use the other value, does it make a difference? No, it doesn't make a difference. So that answers your question. All right. Now, find the volume of the solid generated when R is revolved about the x-axis. When you get your answer booklet for the exam, it will actually be marked, it will have question number 1 and then some blank space marked with A, B, and C. The work for A needs to go into place for A. They will only grade stuff in A for A. If your stuff for A is elsewhere, I'm sorry. So we go to the spot for B and we start work on B. And here we go back, and we're going to need a different representative rectangle because now we're looking at a radius that goes all the way to the axis of revolution. And if you see what I see is we have two different curves, a big R and a little r right there. And so we're going to express the volume in terms of our Shell's method. Volume equals pi integral of big R squared minus little r squared times dx. I strongly encourage writing the form. They don't give a point for it, but it helps focus your mind a little bit, because now we understand we need to find big R and little r. And we want to write the big R and the little r. What is my big R, Matthew?
1 plus sine 2x.
It's 1 plus sine 2x minus the axis, which is 0. And what is the little r?
E
E to the x over 2.
Oh, wait.
And therefore, the volume is pi times the integral from the first x to the last x, which we finally figured out is 1.356, of big R squared minus little r squared. And I can enter that exactly as written. Go ahead and find that integral. And what value do you get when you integrate, Catherine? Pi times 1.3581. I often package the pi into my integrand so that the whole thing just comes out as a number. Did anybody do that, or does anybody have a complete numeric value? What's that? Which one is right?
Both.
That's right. Either one of these is correct. Either way of doing it is fine. The hazard in not packaging the pi in your integral is sometimes people will forget the pi. So that's the reason I just put the pi into the integrand. Questions on that?
So when you do it on the computer, on the calculator, you just put pi and then half in and then write out the whole thing.
You can do that. Or you can, I usually integrate through the y equals in the second calc. So I just let y1 equal pi times the inverse. It's a constant multiple, so I bring it to the inside.
Okay.
Yep. Now part C. And in part C, they say that the solid, region R is the base of a solid. For this solid, the cross sections perpendicular to the x-axis are semicircles with diameters extending from y equals f of x to y equals g of x. Find the volume of this solid. One of the things that you want to learn about the AP language is that they will include values in order to be, they will include words in order to be careful, but those words do not affect the way in which we think about the problem, except to make sure that we're on the right track here. And that's the case here. They talk, let's just translate it phrase at a time. For this solid, the cross-section is perpendicular to the x-axis. So I'm going to do a cross-section. The cross-section stays within the base, right? Perpendicular to the x-axis are semicircles So I draw my cross-section, a semicircle here. And this is this here. With diameters extending from y equals f of x to y equals g of x. That phrase simply means that we have drawn our representative rectangle correctly. Here, that I've got my diameter from f of x to g of x. Okay? And so now they want us to find the volume of this solid. So I'm going to begin by writing the form. Volume is equal to the integral of area times dx. By writing the form, that helps focus my mind a little bit. What is the area of this semicircle? Well, we remember Catherine's clever moves the other day. The area is going to be 1/2 of the area of a circle, which is pi r squared. That means I need to find the radius. And the radius is half of the diameter, which is, in this case, top minus bottom. Notice that I wrote it like this, but I could also have written it, well, half of. Notice that I wrote it like this, but I could also have written it in terms of the curves. 1 plus sine 2x, is that correct? And either way is fine. So bringing our area back over to here, I have volume equals 1/2 pi times the integral of all this mess. Squared. It looks yucky, and so I'm a little intimidated. Yes,
So you need your limits to be
I do. What are those limits going to be?
0 to 1.135.
Yep. Just like so. This looks a little bit yucky, and so because it looks yucky, I'm just going to go back and double check, make sure I did everything right. First of all, semicircle, yep. Second of all, the radius of the semicircle should be half the diameter, and the diameter is the distance from F to G, so that's correct. And this is F, and that is G. Double check, yep, yep. And so there it is. And now all we need is an integration, yes.
So 69 wasn't the radius of half.
Well, can you see geometrically why it,
Yes.
why it is so? Yep. So we need an integration. Seems a little large. What'd you get?
0.077.
Yeah, that's right.
I can tuck it in and talk to you. Just clear it up.
first photo?
You can do that, or you can do the half pi first. 5, 5, and then do function n.
What happens if you round to more than 4 decimal points? Or if you, yeah. If
You
you go like,
round to more, like you go up to 5 or 6 places?
yeah.
No problem.
I was like, I just get these.
Lindsay, you found that.
I didn't know how many.
1.5 is bigger than 1. Bigger than 1.
Like, use your hair.
When you integrate it with that. Probably you have too many parentheses. So check it. This parenthesis should match that one. That one should match that one. That one. This matches that one. But it should actually be there because you want this whole thing to be divided by 2, right? And there's your problem. You actually close that off. You want this whole thing to be divided by 2.
Mr. Hair. Let's say you round it, like you got an answer and you round it and it's like, let's say 0.0770. You just write 0.777, or do they want you to write 4 decimal points?
Actually, you're going to see it in just a moment. Okay? Lindsay, did you find it? Yeah, yeah. Parentheses are the bane of existence. If you happen to be lucky enough to be using a TI-84 with the pretty print algebra, then you should be in good shape. What do we have with an error? Let's see why. So you hit second entry. Oh, you didn't include an X.
Oh.
It's still a heavy. Usually, it's because you have too many parentheses. So let's not overdo our parentheses. So we have all of that. Square. Yeah. See that brace right there? That brace. Being crazy with parentheses. So you should have all of that should be divided by 2, right? And then oh man, I didn't save all these parentheses. And then all of that should be squared. Fine. Yeah, there you go. What a pain that is. You gotta watch your parentheses carefully to make sure that you're grouping the things that need to be grouped. So go back and look through that to see how that reads. Questions on this? Notice that wrangling that final answer out of your calculator correctly was the hard part about this, as it turns out. It was the 9th point. Okay, now let's take a look at how it would actually be scored. Everybody flip the page over. And here we have the scoring guidelines. And the first thing you note is that they find the intersection point, and they label that intersection point S, T. You can do that, by the way, if you want to, so that you don't have to keep on writing the same decimal point over and over again. Unfortunately, your calculator won't know about it, but here it is. And they give the intersection point. They actually give 5 decimal places on that. That's not necessary, but you can do that if you want to. That answers your question about that. And then on the right-hand column, they give the points. And it says that you get 1 point for having correct limits in an integral in A, B, or C. In other words, if any one of your integrals are the integral from 0 to 1.357 of anything dx, you get points. Or even if you, somewhat foolishly, decided to define it in terms of y, if you integrate from 0 to 1.7645 of anything dy, you simply get a point for having the right limits of integration somewhere in there, which is nice. Unfortunately, because of transmission errors, we had 1.1256 for our first thing, so we would not get that point. But the grader would use the value, the intersection value that we got, to then compute all the integrals from there. And if we did them correctly, we would get the subsequent points, even though our numbers are different from your numbers. Does that make sense to everybody? So it's not going to kill us if we get the wrong limit of integration, but we would miss that point. Okay, so we give ourselves 1. And the way we're going to mark it, when you check your papers, you're going to actually mark 1 next to that correct thing here, so you can go back and count up points later.
How close does that to be? How many decimal units?
It has to be good to 3 places. So 1.135 is okay, 1.136 is okay.
Right.
Nothing else will do. Now, in part A, they ask us to compute the area, and they give 1 point for the integrand. The integrand is this guy right here. And if our integrand is exactly their integrand, either f of x minus g of x, or 1 plus sine 2x minus e to the x over 2, either one of those gets you the integrand point. Yes?
What if for the limits of integration, if you had a wrong limit for one of the limit, but then you correct it? Like,
Then you would still get that 1 point because you had it somewhere in A, B, here's the operative word, or C. Yeah. Little math words matter. Or is not English. And so then they carry out the integration. Notice how they present the result. They present it as 0.429, indicating that anything that is 0.429 something will do. Or 0.430 will do. Okay. You get 1 point for the integrand. So as I'm marking this, I'm going to underline the integrand and give myself 1. And you get 1 point for the right answer. So I get 1 there. So far, we've racked up 3 points. Now we come down to B. And in part B, they give 2 points for the integrand and 1 point for the answer. 2 points for the integrand is kind of interesting. They say -1 each error. Here's what this means. The correct integrand is this guy right here. And there are several places to go wrong. Notice that the integrand also includes the constant pi. So I might forget the pi. Don't forget the pi. We like the pi. I might also dork up one or more of my radii. A popular mistake is to do curve minus curve, right? And so I might dork that up. For each error, they're going to subtract 1 point. They will not subtract more than 2. You can't lose more than 2 points for a 2-point thing, right? So I go through here. In my case, I got both points. So I'm just going to mark myself for the 2, just like that. And then we get 1 point for the answer, which is either 4.266 or 4.267, or anything numerically equivalent to one of those 2 numbers. Not all possible answers are shown here. If you get something in terms of pi, and the answer key doesn't have that, then check and make sure that maybe you got it right in there. So this gives me 1 point. So I'm up to 6, and that's happy. And then for the third part, they give 2 points for the integrand. Again, they do not say -1 each error, so that leaves us guessing as to exactly how we would award points. Basically, they're going to look for something that is either right on, is very close, but they missed a factor of a half. For example, a common mistake might be to use diameter instead of radius, or to forget the half pi here. Then you would get 1 point for that. And then if you're way off base, you get nothing. So here we get 2 points for the right integrand, and then 1 point for the answer. Usually, a problem will have 1 point that's hard to get. And it turns out this last point was hard to get because entering this expression in the calculator with the right parentheses was tough. Yes? Point 0776 is within plus or minus 0.001 of the correct answer. So you would actually even, well, okay, yeah. Now, the answer points are only awarded if you are eligible for them. How do you be eligible for the answer points? By having something that is reasonably close to the correct integral in the first expression. If you have no idea and you just write that the answer is the integral from 0 to 1 of 1, and then you successfully integrate that and get 1, you will not get the answer point. So to be eligible for the answer point, you had to pick up all or most of the points in the integrand, and then evaluate your integrand correctly. Does that make sense? Question?
So like, if your integrand is wrong, but your answer's right for your integrand, you don't get the point? Or you do?
If your integrand is way, way off, you're not going to be eligible for the answer point.
But if it's somewhat close and you don't get all the points for that,
Yeah.
and it's the right answer for that messed up integrand,
Then you would get the answer point.
All right.
Different problems will have different criteria for what makes you eligible. So basically, probably if you picked up 1 point here, then you'd be eligible for the answer point here. Now that we have successfully marked up our paper, we're going to go back to the top of our paper. We're going to write our score. 9 out of 9. Yay! If we did not get 9 out of 9, maybe we should mark it as 8 out of 9. If we did not get 9 out of 9, you're going to mark whatever score you got. You're getting credit for doing it, so and it's not like it's inflating your score or helping in any way or another. You simply want to be honest with yourself about how well you're really doing. Now, I'd like to take a look at a sample student response. The first one is a perfect response, so we're going to skip that. If you flip to the next page, and then page following, you see a perfect answer. The thing to note about the perfect answer is that they, like Catherine, did all their answers in terms of pi, and that's totally cool. Let's go now to the next one and see if we can identify how many points this person would get. We're on page B1. Place. It says B1 at the top right. Identify for me. How many points would the person get on this page? For part A. Do they get the 1 point for correct limits of integration? Yes, 1 point there. Correct integrand? Check. Correct answer? Check. Put a 3 right there.
Wait, hang on. Do we have to put unit squared?
Nope.
That's
That's apparently their teacher had them do that out of carefulness. Maybe he's a physics teacher. And there it is. Next page.
Wait, wasn't that only worth 2?
It was worth 2, but also you get the limits of integration point. So we'll just mark that right there on the page. The first point was awarded for correct limits of integration anywhere in 8 years. All right, how about for part B?
No.
What's that? Do they have the correct integrand? No. Where did they make a mistake here? They did curve minus curve for that first radius. Darn it, darn it, darn it. So they're going to get -1 out of 2. So that would be 1 point out of 2. Do they get the answer point? Well, we actually have to punch it into the calculator and find out if they get the answer point, if they are eligible. Let's assume they're eligible, and you punch it in the calculator, and I don't know, but my guess is it's probably right. You want to check that for us? And so we're going to give them 2 out of 3 for that work. Okay? Next part. Part C. Do they have the correct integrand? What's wrong? Did they? Looks good to me. Looks identical to what we have. Sure, but that's because they squared 2. If you take a look at what they have written, we have all of this squared, and they have that squared over 4, which is algebraically equivalent. So they get 2 points for the integrand. How about the answer point? They got a different answer. So they did not get the correct answer.
I don't think so.
He's working. The answer's wrong. Okay. So they get 1 point for B, they get 2 points for C, for a total of 6. 6 out of 9 is still pretty good. I'll see you tomorrow with your completed and checked properly in hand. Don't show up without them.